So the first talk is application of nanoantennas and metamaterials from information processing and imaging to light harvesting for energy conversion. It's going to be presented by Professor Stefan Maier, Chair in Experimental Physics, Applications of Nanoantennas, Chair of Experimental Physics at Imperial College, London.
Okay, thank you very much. It's very exciting to be here. It was also really nice to see a presentation about the vision of the Institute and just seeing all the different research fields you are in the process to establishing there. I think actually metamaterials can be at the heart of many of them. And I also think, just as a side comment, because I might forget that later on, that the combination of energy research and smart materials and metamaterials research is a really fruitful field for the future. So I congratulate you now already in the way you are setting this up. Thanks for inviting me here. So I was thinking about what to talk about, and I have chosen a couple of topics that I think you will find interesting from a application viewpoint mainly. So I hope you will find this interesting, but let me first maybe quickly just tell you a little bit about myself and our group. So we are at the moment actually mainly at the University of Munich. So there's a new institute in Munich. It's called the Nano Institute Munich, which is an expansion of the physics campus of the University of Munich, which you see here, and that is where we are currently based. I also at the moment still have a temporary part-time appointment at Imperial College, where I was for a long time. So as you might hear from my accent, originally I'm from Germany. So I did my undergraduate education in Munich. Then I moved to Caltech, where I did a PhD and postdoc in the area of plasmonics. Then moved to the University of Bath. So that's right at the border between England and Wales. Very nice, small university. And then in about 2007 at Imperial College London, where I've been full-time until 2 years ago, and now, as I said, part-time. And the main part of the group is in Munich, where we have most of our new facilities. Everything that I'm going to present now is mainly due to the people in my group. I'm just putting a couple of here up. So I believe one of the very interesting aspects, well, of academia in general, but of an interdisciplinary field as metamaterials in particular, is that it's really a great ground for educating the most brilliant young researchers. So these are people that have been in my group over the years and that have now obtained either faculty positions or permanent positions in government research labs. And you see we are well established. So my alumni all over the world, and that's really one thing that I'm mostly proud of, I think, actually, from our research. And I think you have really a great opportunity with your center to do something similar, not only for research, but also for education locally. So I think the educational aspect of that field is really, really great. And you see, so one of my alumni is actually a professor now, relatively close to you. Okay, so what do we do in my group? So we have two fundamental research strands. So one is more nanoantenna research. So there we look at the building blocks of metamaterials. These are either dielectric nanoresonators made out of prominent semiconductors, either silicon or 3-5 semiconductors. Here we also work a lot with a group of Riccardo Sapienza at Imperial College London, who will talk a little bit later. Then we work on plasmonics, mainly for surface length sensing and spectroscopy. So traditionally, the group has done a lot of work in biosensing. Something relatively new for us, but what I think is a very promising field is energy conversion, actually, based on nanophotonic structures. I'll say a little bit about that later on. And then, of course, all of these nanotechnology enabled ways of confining light, of course, lend themselves exceedingly well to couple light into two-dimensional materials, for example. So nanophotonics is really the basis of many new device possibilities that we have. And one of those device possibilities are, of course, metamaterials, where we now take such units and combine them into larger scale area to get new photonic functionality. And that is the second strand of my group. And that's where I will focus on today, since I thought I make the talk a little bit more application focused maybe. So I will present you examples for metamaterials for holography, particularly for holographic video display. And very briefly, I show you some unpublished research that we just finished literally a few days ago of metamaterials for telecommunications. And I should say, so with these two topics, that will be the main part of my talk. Everything that I show you from the list of equipment that I have seen that Dr. Alteneji put up, you can already do that there. So all of this was actually physically written with this 3D direct laser writer that I think I saw on one of your slides that you already bought. So very good choice there. And then in the second part, I will tell you a little bit about how we can combine metamaterials ideas for light harvesting in a context of energy. Yeah, and then we also have a fiber program together with the Leibniz Institute in Jena, where we make metamaterial fibers, so light cages, as you see here, but I will not speak about that today due to lack of time. So the main two topics, as I've already said, will be metasurface holography, which is what I will start with now, and then plasmonic light harvesting for energy. So let's get right into it. I'm not going to give a big introduction into metamaterials here. I just want to highlight that what do metamaterials allow us to do? They allow us basically to achieve sublime control over the way we can steer light at interfaces. Yeah, we can have complete amplitude and phase manipulation of light when we take an interface and when we nanostructure it. This is probably one of the seminal papers there by Federico Carpasso's group from Harvard that basically shows how we can, via nanostructuring such an interface into either resonator units or into non-resonant units, where we rely on geometric phase, where we can basically set up a complete phase and amplitude profile at such interfaces, and this way steer light in really unexpected ways. And the interesting part here now, from an application viewpoint, is that the pitch distance between all of these units can be way below the wavelength, meaning that if I make a device out of it, and if I want to use these units, for example, as pixels, it allows me sub-wavelength pixels, and it gets rid of the problem of higher diffraction orders. And one application that comes to mind for this, then, of course, is the digitization of information. So if we think about computer-generated holograms, such metasurfaces might actually be an ideal way to achieve a large information capacity. And that's what I want to focus on now. I'm not going to have the time to go into the details here about holography with metasurfaces. There's an excellent review in a journal called Nanophotonics, actually, by the group of Xuan Zhang and Thomas Zenkraft just a couple of years back. So for the audience, if you are interested in that, this is a really good starting point. Yeah, I just want to highlight two early works, one work here coming out of Cambridge, one work coming out of Birmingham, which basically shows two different ways of how you can digitize a computer-generated hologram with a metasurface. You can either do it via resonant nanoantennas. So this work used, for example, two metallic nanorods in perpendicular orientation to each other, and the arrangement of one rod was used to encode one image. The arrangement of another array of rods was used to encode the other image. Yeah? So what you basically do is you take your computer program, you generate your computer-generated hologram, so your amplitude faceplate, and then you encode it into these little nano antennas. And due to the highly anisotropic scattering response of such antennas, you are then able to pack, in this case, two holograms in two different encoding arrays that can have a sub-wavelength distance from each other. You can also do the whole thing not relying on resonance and do it dispersionless and make so-called phase-only metamaterials, where you rely on the geometric phase that you impart on a beam of light as you guide it, as you transmit it through a transparent plate that has such a surface structure on of it. Yeah, this is the so-called Parahatman-Berry phase, and it's one of the main working horses at the moment to make to make holograms based on meta surfaces. What I want to focus now on is on the way on exploring how can we increase the information capacity of such a hologram. So what we want to do is basically multiplexing. We want to make we want to make one metasurface hologram plate that can have many pictures encoded in it, or like in our case, actually what we want to do is we want to use it for holographic video displays. And for that, you need to choose a degree of freedom where you have many orthogonal modes, yeah, so that in each mode you can encode a different image. And what we choose to do that with are so-called orbital angular momentum modes. So these are light beams that have a helical wavefront, as you see here. So they have a topological charge greater than 0, and you have in principle here an unbounded set of modes available. So like an infinite number of modes that you could encode images with. The only problem is if you take a usual metamaterial hologram, so like a faceplate such as this. In the first part here now, I will, by the way, I should say that, speak about phase-only holograms. So if you take such a faceplate and you want to now read out a hologram via a helical mode, via an orbital angular momentum mode, and you look, what do the pixels look like, for example, of this letter A, you see they are unfortunately all scrambled, because traditional phase holograms do not conserve the helicity, the basically pitch of this screw here of your orbital angular momentum modes. And like, why is that the case? So some people in the audience might know a bit about Fourier imaging theory. So if you take a helical wavefront and you take a Fourier transform of it, you get a donut. Okay, and the higher the topological charge of our orbital angular momentum mode, so if you look at my mouse cursor here, you see examples from -2 to 2. So you see the winding ratio basically increases here. The higher the topological charge, the larger are these donuts. And then the problem here is that these donuts basically start to overlap. Okay, donuts in each pixel overlap and you get this scrambling. So like what you need to do in order to make a meta hologram that preserves the helicity of such a beam is you need to sample your image. For example, if we look at this rocket here, you like need to sample it with a Dirac comb array, so with a two-dimensional array with a pitch, yeah, that is basically greater than the distance of this radius here. But if you do that, then you can make a OEM conserving hologram, where you now basically have at each of these pixels here your nice little donut. And then if you have done that, then it's very easy to go from a conserving hologram to a preserving, to an OEM selective hologram. You now just add basically a spiral faceplate of the topological charge of your helicity here. And now you have a hologram that when you now read it out, so like let's say you encode it so that the picture that you want to encode is encoded in a beam of topological charge 2, yeah, then you can now use a beam of helicity -2 in order to get a nice Gaussian pixel, as we know from normal imaging. And then you can now combine multiple of these, and then you have an OEM multiplexing hologram, where you now can read out with a normal Gaussian beam many different holograms that are all encoded into different helicities of your mode. Yeah, so these different OEM modes now carry independent information channels. And now the beauty of a metamaterial here is now, of course, well, you don't need to stop here now. So let's say we have made our nice hologram. Why not add another metamaterial into our code that gives us the final design that has the function of a lens? If you do that, you now have a meta hologram plane that can lenslessly reconstruct an image directly on a CCD. And then in our case, you just need another lens to expand the image a bit. Yeah. So here you see some examples. This was done in collaboration with a group at CNRS in France, where we have encoded 4 different images with a meta hologram based on gallium nitride rods. So these are gallium nitride rods of a height of 1 micron. You see some SEM images here. And basically the radius of these rods, so you see as you change the radius here, you get complete control over the scattering phase of a light beam from 0 to 2 pi, which is what you need to then record these images. Yeah? And then you can then go one step further and then go from these preserving holograms to selective holograms. So here are 4 examples where we added spiral faceplates to select modes either -2, -1, 1 or 2, and then you see we can then only read out these modes, so these images, when we actually illuminate them with the mode of opposite helicity. Yeah? And then finally you can combine all of these then at the end into one hologram, so that you can now read out with 4 different beams, 4 different images. There's a problem here though, and the problem here is that since you only change the phase of your light beam here. These are so-called phase only holograms. So you don't have control over the amplitude of the way the light interacts with your hologram readout plate. You get quite a bit of crosstalk. So like in order to actually get these nice images, what we needed to do is we needed to bias our sensitivity of our CCD in a way that is commensurate with the OEM sampling constants that I talked about at the beginning to get these really nice images. So how can we get around that? And how can we actually not just encode 4 images, but a lot of images? And the way to do that, and that's what we have done here the last year in Munich, is to add another degree of freedom. So you need to make holograms, meta holograms, where you don't just control the phase, but you also need to control the amplitude. And how do you control the amplitude? You control the amplitude now by choosing as the pillars that you have in your metamaterial, pillars of different height. Yeah, so those of you that have worked in metamaterials a bit might think, okay, that's probably not very easy to fabricate, but actually it's not so hard to fabricate, and you have the equipment already. You use a direct laser writer because there you have independent control over the height degree of freedom. Yeah, and our idea then is the following. So we make now a hologram, yeah, where we change the orientation of our pillars and the height of our pillars to both manipulate amplitude and phase of a light beam, of a helical light beam that passes through it. This way we have complete control over the complex amplitude and can now use a large amount of orbital angular momentum modes without crosstalk. So what I first show here now are simulations where we basically take 2 movies, okay, and each movie has 100 frames each, and we encode each frame of these movies now in a different helical beam, and then we generate our hologram. And the nice part is now that, of course, because this works in 3D, we can now say, okay, let's say 1 centimeter away from the hologram, we want to reconstruct 2D movie 1, and 1 centimeter farther away, we want to reconstruct another movie. Okay, so like in our case, we have somebody doing some tricks with like a football now here that we have encoded into beams from -50 to 50 in like one plane, and we have one balancing a basketball, I believe, or maybe it's like also like a football that we encode a little bit farther away here. Yeah, and I should say, so now these are not trick movies. This is actually Fourier imaging theory, yeah, that you see here. Okay. So the main main breakthrough here was unlocking this height degree of freedom. So now just very briefly again how this works. So it works quite similar to what I quickly explained with these phase holograms. So we take each image frame, we convolute it with our 2D diffuser array, and as I said, we need to do that so that our OEM helicity is conserved, so we need to sample. Then we scramble it with a random phase. Why do we scramble it? Because if you have a normal image, yeah, and those of you that like photography know the problem that you are often either overexposed in your highlights or like underexposed in your shadows, because your amplitude in a normal image varies over an exceedingly large amount, right? If we look at a modern Canon or like a modern Nikon, they have a dynamic range of about 12 orders of magnitude. Clearly, you cannot do this with a hologram. So you need to flatten the amplitudes a little bit. So the whites come down a little bit, the blacks come up a little bit, and you can do that with such a diffuser array. Then you have amplitude and phase. Then we add the OEM phase that we want to use for encoding. So this is now a different faceplate for every beam. So let's say frame 1 is beam with topological charge -50, frame 2 is beam with topological charge -49, and so on and so forth. And then we also add a lens on it, yeah, so that we can reconstruct our hologram without a lens. That'll be, for example, nice if you want to use it on like a cell phone, for example. And we can do this now for both of our movies, and we throw everything together in the Fourier domain to get then one amplitude and phase profile of our meta hologram. And this is then what we write. So now just briefly, how much do we digitize here? So we digitize with 64 different levels. So we have rods of basically 8 different heights and 8 different orientations. And if we throw all of this together, what you see here is the real part of the complex amplitude, the imaginary part of the complex amplitude. You see, well, we sample all 4 quadrants. Yeah. So this shows you amplitude modulation versus height and length of such a pillar when we keep the width fixed, and here the same for the phase. And you see we cover all of the phases from 0 to 2 pi, so we are safe, and we also have a nice amount of amplitude modulation. And these are the heights that we actually use. So this this black bar here, these are the heights for that particular length that we use. And then we use this laser writer that you now also have at your institute to write this plate. And like, just to make it clear, so this is just one plate, yeah? So this one plate has all of the information of both of these movies in it. All of the frames are encoded in a different orbital angular momentum beam. And then it's just designed so that the playback of one movie is 2 centimeters away from our plane. And this one here is 3 centimeters away from our plane, yeah? And this is what the plane looks like. So with our machine, that took about 2.5 days to write. I assume if you bought your laser writer in the last half year, you have a version that's about a factor 5 at least faster than we do. Yeah, and here you see an example what this looks like. And then if we had encoded our whole movies in there that I showed you, this would have taken even like longer. So these are just 2 small experimental movies. So here you see a rotating triangle. Yeah, this is a 2000 by 2000 pixel video, and here a rotating spiral. Yeah, so these are the 2 movies that we experimentally encoded. Yeah, so like I believe there's a lot of mileage in using such metamaterials for image processing and imaging applications. And I've shown here you one example that is actually not really difficult to make. You can see more details here, and of course also asked me in this paper that we just published. And then, so like apart from applications for movie playback, just one last slide here on this topic. So what can you use this for? You can use it, for example, for encryption, right? So let's say you have an image here which shows a QR code that you want to encrypt. So you randomly distribute it, let's say over 30 different image shares. Then you encode each share into one orbital angular momentum beam. You use what I just said to make your like hologram. And then obviously you can then only reconstruct your QR code if you tell your like client which beams he needs to use to actually read it out. Otherwise, everything will get scrambled. Yeah, and then just one last application. I will not go into this in detail because my time is already running out. Such laser-written metasurfaces are, of course, also perfect to put on almost everything. Yeah, so for example, here we have put one onto an optical fiber, like to make an achromatic lens. And we use the same trick that we have control over the length of our pillar unit in order to now independently change the phase profile of our lens. So like in this case, we arranged it so that we have a spherical phase profile for focusing, but now of course we can use the width of these elements to change the group delay, and this way we can make this focus achromatic, so we can compensate for the arrival time. And this way we have made an achromatic lens, and I think that's a real important first that shows an almost perfect focus over a 400 nanometer bandwidth on the end facet of a fiber that spans all of the telecom range. And then you can use this, for example, as like an endoscope. So here we have used a US Air Force imaging standard. These are the experimental images down here in order to show broadband endoscopic confocal imaging of this particular sample here with a broadband wide light source of 400 nanometer bandwidth. Yeah, so I think just to finish that up, there's a lot of mileage in using such laser-written metamaterials for all sorts of applications. So now in my last 5 minutes, I just want to quickly give you one glimpse about doing almost the completely opposite. And this now has more relevance for energy. Because of course, we can also use the ideas from metamaterials to actually make disordered arrays and like try to change the way that we can efficiently, for example, harvest light. And like that is what like this is all about, using the power of disorder. So just very like briefly, what do we want to do there? We want to use functional nanoparticles for photocatalysis, okay? And we want to efficiently harvest light over a broad wavelength range into a plane where we have these particles, yeah? Or maybe onto a 2D material that would be underneath here. So now one nice trick if you want to have broadband light harvesting is to use a highly disordered array. So if you just have a highly disordered array of colloids, it has many different optical modes. So think about it has many modes corresponding to different colors that it can harvest light. Yeah? And then one nice aspect of such systems, and that is true actually for any chaotic resonator system, is that all of the lifetimes of all of these modes, if it's a truly disordered array, tend towards a common value. You say they have the same intrinsic lifetime. And why is that important? Because then I can couple to all of these modes with the same strength. This is something, I don't have time to go into this now here, known as critical coupling. But like what it basically means is that if you now expose such an array to sunlight, you will excite, so this eta here is a calculated excitation efficiency. If you're at this critical coupling condition, you will excite all of them with the same strength, meaning you have a broadband absorption. Your like material looks black. Yeah, most famously, for example, moth eye, also called black silicon for solar cells. And now we ask, so how can we modulate this? And now the trick to like modulating here is now that you now say, okay, so now I take one mode and I change its lifetime. Then you couple less efficiently to it, and then that mode will get reflected. And how can you do that? By, for example, putting a simple Fabry-Perot cavity underneath. So here we have a Fabry-Perot cavity underneath that selects for a certain wavelength. So this would be half the wavelength here. And then this mode will get reflected. So that's completely opposite to the normal Fabry-Perot behavior, where, of course, the mode that the cavity is tuned for gets stored. Here it gets reflected. You like might ask now, okay, what does all of this have to do with energy conversion? I will get to that in like one moment. But like, let me just show you what you can now do with this, for example. So this is just an array here of highly disordered silver particles that are just deposited using a vacuum technique. Okay, and if the spacer layer underneath here is thin, so that we don't have a Fabry-Perot mode in the visible, it looks black. But if we make it thicker and thicker and thicker, you see, we get these really bright reflection colors here, because these are the modes that get expelled due to this mismatch with critical coupling. Yeah? So if you then, for example, make such a wedge-shaped structure, you can generate all colors of the rainbow here. You have a really nice gamut. You can reproduce images. This is an original image. This is one that we have reproduced with 4 different heights. And you can this way generate color quite nicely with a completely disordered array that acts in a sense also as a metamaterial. But the real clue now comes here, and this is just going to come out now in advanced materials. It doesn't matter what the colloids are made of. So here, the first slide here is simulations, then one more slide and I'm done. I show 4 different colloids, silver, gold, and then 2 catalytic colloids, palladium and platinum. Those of you that know your optics, you know they have a completely different optical response, right? Gold looks golden, silver looks like silver. Well, these guys, we like know what they look like, at least in like bulk form. So if you would calculate from their refractive index what a single colloid would look like, you know, it would have completely different colors. If we put them on a Fabry-Perot cavity, the colors are all the same. The color is completely determined only by the thickness underneath, which means that the far-field properties and that the appearance doesn't depend on the material. But of course, the local near field around these structures, the near field enhancement, depends very much on the material. So we are now able to decouple the far field light harvesting response and the material response that shapes the near field. So the Fabry-Perot cavity shapes the far field collection efficiency, the material shapes the near field efficiency. And we think that this might be very interesting to use this then as a way to harvest sunlight to catalytic materials for fuel cells, for examples, or for energy. And here, this is my last slide, just an experimental demonstration here with these 4 different materials. Let's just look here. So we have our cluster array. This is the Fabry-Perot layer. We have a little mirror at the end here to get nicer colors. And you see here, these are 4 different thicknesses here. And you see that for all 4 materials, the external appearance is completely the same. Yeah? So if you want to make an energy harvesting material that also looks good, so to speak, you want to have it be red. Yeah, this is how you can have the color that you want, but have the underlying functionality completely decoupled from the color. Yeah, and this allows then basically us to use, we believe, such nanostructures then for efficient energy conversion. But I'm not going to go more into that now because my time is running out, and I just want to thank my collaborators here. So the work that I've shown you on the holography was actually mainly done by Hao-Ran Ren, Humboldt fellow in my group, and it was in collaboration with Patrice Genevet, Yunso Gro, and Markus Schmidt for the fiber. The work that I just presented now on the light harvesting by Shangzu Lu, also Humboldt fellow in my group, mainly in collaboration with a group of Shangzhang. And with that, well, I hope I've given you a glimpse of what at least we do with Metamaterials, and I hope you find this inspiring and yeah, maybe take it on board and we see what we can do together there in the future. So thank you very much.
Thank you very much. Very interesting talk, Professor Maier. We have one question. It's from, the question is, what are the characteristics of the read and write laser sources? And can the read and write system be portable?
Sure. So I assume you mean for the holograms, right? So let me just go back here. Yes, certainly. So I mean, we like to do everything on like a lab table, right? But what you need to, so you both read, well, so you read with a helical beam, yeah, and you do not need a beam for writing. Yeah, this is a computer generated hologram. Yeah, so you need, so like don't think about, you know, like old style holography where you use interference between two beams to write the hologram. So here you generate this faceplate in a computer. So all of this part here is a computer code that gives you then, for all of these images and all of these different Fourier distributions here, gives you one amplitude contribution and one phase contribution. And then the only thing that you then need to do is now to ask, so how do I now encode that? Basically this, how do I encode this into this, right? And then you take a laser writer to write it. And then in order to read it out and now answer your question, all you need is a laser source and a spatial light modulator. Yeah, so something like a good resolution LCD display that can basically give you these modes, right? This is what you need to like generate. Yeah, but that's like standard. So that costs, well, a good quality one for lab costs a couple of $1,000 US. But of course you could like miniaturize them.
Yeah. Thank you very much, Professor Maier. Very interesting talk, and I'm really surprised of these results. Very nice. Thank you very much.
Yeah, thank you very much.